So, let us continue with the previous class. In the previous class, we were doing one example on sensitivity analysis, that is for changes in the parameters in the coefficients of the LPP problem, what can be the possible effect on the optimal solution of that particular problem. The last one which we have is which resources should be increased or decreased to get the marginal increase of the objective function. So, the which resources should be increased or decreased to get the best optimal marginal index of the increase of the objective function. If you just quickly let us recall, this was the original problem, maximize z equals this 3x1 5x2 plus 4x3 subject to these constraints. Basically, you are producing three type of products, capital X, capital Y and capital Z. Their unit prices are given as 3, 5 and 4. And for this particular problem, if you recall, your solution was this table. The last table was the solution, that is x1 equals 7 by 3, x2 equals 5 by 3, x3 equals 0 and z star was 46 by 3. The basic variables was here x1 and x2 and the others were the non-basic variables. So, this was the initial optimal solution. So, from here if you see the problem now, which resources should be increased or should be decreased to get the best marginal increase in the objective function. Now, from optimal simplex table, if you see from optimal simplex table, the value of Z4 minus C4 is 7 by 3 and Z5 minus C5 is 2 by 3 from the optimal table. So, here we have written Z4 minus C4 is 7 by 3 and Z5 minus C5 equals 2 by 3. These values we are denoting as shadow price of resource 1 and 2 respectively. So, these are the positive values. So, we have taken these and we are saying that these are the shadow price of the resources 1 and 2 respectively. Now, increasing the amount of resource 1 and 2 will increase the value of the objective function by 7 by 2 and 2 by 3 respectively. So, if I increase the amount of resource 1, then the objective function will be increased by 7 by 3, whereas for resource 2 it will be increased by 2 by 3. Now, suppose delta B1 be increased in the first resource of the B1, that is if B1 is the initial resource and we are increasing it by delta B1. So, that B1 becomes B1 plus delta B1. So, in this case your increase in delta B1 is the increase in B. Now, your XB star this is equals B inverse B star. This value of B star or in other sense x1 x2 this equals I can write down from here the corresponding value I have to take here, this I have taken as x4 and x5. So, B inverse matrix is nothing but this one, this is your B inverse 4 by 3 minus 1 by 3 minus 1 by 3 and 3. So, here we are writing this one as 4 by 3 minus 1 by 3 into minus 1 by 3 and the last one is 1 by 3. And your B value will be increased, B will be increased, this is 4 and this one will be 4 plus delta into 4 plus delta B1 and this one will come as 9. So, this is your B inverse into B star you are writing the 4 plus delta B1, original value was 4, B plus delta B1 and for the second one the value from this table it is this is 9. Your second resource was 9 and first resource was 4. So, this 4 has been increased to 4 plus delta B 1 and this has become 9. So, that this equals you can write down 7 by 3 plus 4 by 3 into delta B 1 and 5 by 3 minus 1 by 3 into delta B 1. Now, this x 1 x 2 this value should be greater than equals 0. That means, individually these two should be greater than equals 0. So, that 4 delta B 1 plus 7 divided by 3 should be greater than equals 0 and minus delta B 1 plus 5 by 3 should be greater than equals 0. So, from here you are getting delta B 1 is greater than equals minus 7 by 4 and this one is minus delta B 1 is greater than equals minus 5. If I combine these two, then minus 7 by 4 is less than equals delta B 1 less than equals 5. So, I can write down original value was 4. So, 4 minus 7 by 4 less than equals B 1 plus delta B 1 which is less than equals 4 plus 5. Or in other sense, this implies your 9 by 4 less than equals delta B 1 less than equals 9. So, from here it is quite clear that since the range is 9 by 4 to 9, if the value of the first resource B 1 is increased from 4 units to maximum limits of 9 units, then the objective function, the optimal solution will remain the same, there will be no change. So, for the first resource from the original value 4, this was the original value was 4. From the original value 4, if we increase it up to 9, there will be no change in the optimal solution. In the same way, now let us check the second one, that is B 2. Resource B 2 means this value. If this value, how much we can change? So, your B 2 say becomes B 2 is changed to B 2 plus delta B 2. Suppose I am making the change. So, again following the same steps, x b star equals B inverse B star. From here I can write down x 1 x 2. This is equals to, again this one will come 4 by 3 minus 1 by 3 minus 1 by 3 and 1 by 3. So, this will be 4 by 3 minus 1 by 3 minus 1 by 3 into 1 by 3. Here, for the earlier case, original value of resource 1 is 4, whereas original value of resource 4 is 9 and there is an increment of delta B 2. So, that you will get this thing. So, this value will be equals to 7 minus delta B 2 divided by 3, 7 minus delta B 2 divided by 3 and next one will be 5 plus delta B 2 divided by 3. So, we are getting this thing. Now, for feasibility this should be greater than equals 0 and if we get this one from here just following the earlier method, that is following the same method, you can get the lower bound and upper bound and you can, if you combine both of them, then ultimately you will find 4 less than equals B 2 star, which is nothing but which is equals to B 2 plus delta B 2 is less than equals 16. So, that you can say that this value always actually this should not be delta B 1, B 1 plus delta B 1. So, this I can say B 1 star. For the earlier case it will be not delta B 1, but B 1 star and here it is B 2 star. So, B 2 star can take the value from 4 to 16, or in other sense its original value of resource 2 was 9. If you increase it up to 16, then also the problem the optimal solution of the original problem will be as it is. So, like this way, whenever I have the original problem, I can see how much deviations can be given, so that the optimal solution will remain same. I do not have to calculate it again, and I have to find out the optimal solution. Now, next come to the next topics, that is introduction to duality theory. Every LPP has a corresponding mirror image formulation, which is known as the dual of that LPP. So, please note this one. We are saying that every LPP has a mirror image formulation. That is, if you keep it on the mirror, then the image formulation will be like that. If the original problem has n variables and m constants, then its dual will have m variables and n constants, as we have written here. So, please note this one, that if the original problem has n variables and m constants, then its dual will have m variables and n constants. If a given LPP can be thought of a resource allocation model, that is, in which the objective is to maximize the return or profit subject to some constants. This is the original LPP. Usually, we always say LPP as a resource allocation model, where I have to maximize the objective function, which may be the return or the profit subject to certain constraints on the composition of resources subject to this one. Then its dual will correspond to an LPP, which will minimize the consumption of resources subject to some profit maximizing constraints. So, basically, if you are maximizing a return or profit subject to certain constraints on consumption of resources, then its dual will be the opposite one, that is minimization of the consumption of resources subject to profit maximizing constraints. So, when an LPP contains large number of constraints and smaller number of variables, then computational effort can be largely reduced by converting it into an dual problem. Please note this one, that why should I go for the dual problem? Because ultimately, if you see in the dual problem as well as in the original LPP, in both case your optimal solution will remain same, optimum solution will not change. So, one reason for going for dual LPP is that if I have a large number of constraints, then to find the feasible solution of that large number of constraints is time consuming, and computationally it takes more time. Whereas, if I have smaller number of variables, if I convert it into the corresponding dual problem, then what will happen? My large number of constraints will go to the minimization one, and since there was smaller number of variables, so number of constraints will reduce. So, our aim is, if I have less number of constraints, then my solution I can get quickly, or computationally it will take much less time. That is one of the basic reason for converting one original LPP into its dual form, and then find out the solution of the dual problem, and then again try to find out the solution of the original problem from the dual problem. So, please note this one, if I have a large number of constraints, whereas number of variables are less, in that case it is beneficial to convert the original problem into its corresponding dual problem, because whenever I am converting it into the corresponding dual problem, then number of constraints in that case will reduce and number of variables will increase, and since number of variable constants are less, therefore, computational time will be much less. So, some interesting properties on dual LPP. Number 1, any feasible solution of a dual model provides a bound of the objective to the original primal problem. So, any feasible solution of dual model provides a bound on the objective to the original primal problem. Optimal solution of dual equals to optimal solution of the primal problem. Please note this one. Optimal solution of a dual is equals to the optimal solution of a primal problem. Third point is dual of a dual model is once again the original primal model. That is, you have the original model, you are taking the dual of the problem, then on the dual again if you take dual, you will get back the original model. So, we can say that your primal dual formulation, you have the primal problem, either you can write it in this form, minimize CTX, that is minimize CTX subject to Ax greater than equals 0, where its dual will be maximize B transpose Y, some new variable we are writing. So, here the resource will be this one B transpose Y subject to A transpose Y less than equals this C transpose. Similarly, if we have the maximization problem, whatever we are doing in general, maximize C transpose X subject to Ax less than equals B x greater than equals 0. This will be converted into a minimization problem. Minimize B transpose Y subject to A transpose Y is greater than equals C transpose. So, please note that if the original primal problem is maximization, its dual will be minimization, whereas in the subject to condition, if Ax less than equals B, in that case it will be greater than equals constants will come, and this coefficient will be from the objective function, that is A transpose Y is greater than equals C transpose Y. So, for the canonical form of the primal and dual problem can be written like this. You have the problem maximize Z equals C1 x1 plus C2 x2 like this way plus Cn xn subject to ai1 x1 plus ai2 x2 plus ain xn less than equals bi, where your I lies between 1 to n. I lies from 1 to m and xi greater than equals 0, where your I is equals to 1 to like this way, it is n. So, x1, x2 are called or known as the primal variables. x1, x2, xn we call it as primal variables, and this z we call it as the primal objective function. So, these variables x1, x2, xn are primal variables, whereas z is the original objective primal objective function. So, the corresponding dual of this problem will be, since it is maximization problem, so it will be now minimization. So, the function will be changing w equals, I can write it summation I equals 1 to n bi into vi, some new variable, summation I equals 1 to n bi into vi, and this one subject to, this will be 1 to m. So, subject to aj1 v1 plus aj2 v2 like this way, ajm bm, since this was less than equals, so it will be greater than equals cj, where j will be from 1 to n. So, basically if you see, and of course, V I greater than equals 0, where I is equal to 1, 2 like this way up to m. So, in the original primal problem, you had n variables and you had m constraints like this. The n variables was x 1, x 2, x n. Since you have m constraints in the original problem, therefore, in the dual problem, you will have m variables which we are denoting as V 1, V 2, V m, and the number of constraints will be n. Here j is varying from 1 to n. So, subject to this one. So, if the constraints are inequality type, that is greater than equals or less than equals type, you can always convert it as usual by changing greater than equals into less than equals. Or if you have equality type, then this equality type you can convert it into two types, two inequalities, one by making greater than equals, another by making the less than equals type, which we have discussed this one. So, this we will assume as the standard canonical form of the original problem, and if it is not in the canonical form, first I will convert my LPP into canonical form, and then I will write down its dual in this particular format. So, please note that this primal and dual problem, they are consisting of constraints with inequalities. They are always called symmetric LPP. They are known as symmetric LPP. So, please note that primal and dual problems consisting of inequalities are known as the inequality constraints are known as symmetric LPP, whereas if the primal primal LPP has only equal type of constraint, then we call it as unsymmetric. We call this one as unsymmetric LPP. So, please note this one. If the inequality, if in the constraint you have greater than equals inequality or less than equals inequality, then the primal and dual problem is known as symmetric LPP, whereas if the constraint or contains only equality type, then we call it as unsymmetric LPP. Now, see two theorems over here. If any constraint is primal, if any constraint in primal is strict equality, please note this one, is strict equality, then the corresponding dual variable is unrestricted in sign. So, please note this one. In the primal problem, if any constraint is there which is of equality type, then the corresponding dual variable will be the unrestricted in sign. Similarly, if any variable of the primal model is unrestricted in sign, then the corresponding constraint of the dual will be of equality type. That means, these two are opposite ones. In first theorem says that if any constraint in the primal problem is of equality type, then the corresponding dual variable corresponding to that constraint will be unrestricted in sign. Similarly, if any variable in primal model is unrestricted in sign, then the corresponding constraint of the dual problem will be of equality type. So, now let us see how to convert a particular LPP into its corresponding dual problem. Let us take this problem. Maximize z equals 3 x 1 plus 2 x 2 subject to 3 x 1 plus 4 x 2 less than equals 22, 3 x 1 plus 2 x 2 less than equals 16 and x 2 less than equals 3. If you note, the problem is already maximization type and all the inequalities are less than equals type. That means, this particular problem is in canonical form, since I have 3 constraints in this. So, in the dual problem, in the objective function, there will be 3 variables, since I have 3 constraints here. So, let V 1, V 2 and V3 are dual variables. So, I am assuming V1, V2, V3 are the dual variables. So, what is the problem? Now, maximization will be converted into the this one, minimize W equals, what will be the objective function? The objective function is 22 V1, 22 V1 plus these B values 16, 22 V1 plus 16 V2 plus 3 V3, subject to, I have to take these rows, first row here, that is first constant is corresponding to the variable V1, second constant corresponds to V2 and third constant corresponds to V3. So, I have to write down 3 V1 plus 3 V2, but for x1 nothing is there in the third constant. So, basically what you are writing, the coefficients of the variable x1 in each constants, and you are associating with the variables V1, V2 like this. So, for the first one it will be subject to 3 V1 plus 3 V2 greater than equals value of Cj. Here the corresponding to x1 variable is 3. So, here it will be 3. Similarly, for the next one it will be 4 V1 plus 2 V2 plus 4 V1 plus 2 V2 plus third constant corresponds to the variable V3. So, plus V3 greater than equals the coefficient associated with the variable x2, that is equals to, and obviously V1, V2, V3 greater than equals 0. So, the dual of this one original problem is this one. So, if I take this thing, so I hope it is clear that whenever you are taking the dual problem, then the minimize maximization problem will be converted to minimization, and minimize W equals how many variables will be there? It depends how many constants you have. Since you have 3 constants, so I am writing 22 V1 plus 16 V2 plus 3 V3, subject to, for the first column, of the constants you are taking, you will take the coefficients. Here it is 3x W 3 V1 plus 3 V2. For the third constant there is no coefficient for x1 is 0. So, 3 V1 plus 3 V2 greater than equals 3. This 3 is coming as the x1 is the coefficient of x1 in the objective function is 3. Similarly, you will take the second column, that is 4 V1 plus 2 V2 plus V3, which is greater than equals the coefficient of x2, that is 2 in the objective function. Again, if you take the dual of this problem now this problem has how many constants? You will see this problem has 2 constants. So, it's this dual of this problem will have 2 variables. So, I can write down, since it was minimization, it will be maximization. Maximize z equals 3 x1, from here it is coming, plus 2 x2, subject to what happens? Subject to 3 x1 plus 4 x2, 3 x1 plus this 4 corresponding to V1 coefficients you are taking, 3 x1 plus 4 x2, this will be less than equals because it was greater than equals, less than equals coefficient of V1, that is 22 in the objective function. Now, take the second column, that is column corresponding to V2 in the coefficient, that is 3 x1 plus this is 2 x2, which is less than equals the coefficient of V2, that is 16 in the objective function. Now, you take the third column corresponding to V3. Here it is only x3 will come, x2 will come, x1 and x2. In the first one V3 is not there. So, x2 less than equals, this is coefficient of V3 corresponding to in the objective function, that is 3, and your x1, x2 greater than equals 0. And if you see this problem is nothing but the original problem. Therefore, dual of the dual gives you back the original problem. So, I hope it is little clear. In the next lecture, we will solve 1-2 more problems on this.